Okay, welcome back. And today we're going to continue on with Chapter 8. And we're going to deal with confidence intervals. And last time we dealt with confidence intervals involving where we're talking about the confidence interval for a population mean when we know the standard deviation. So we're going to continue on with that. We're going to make some comparisons, and then we're going to go on to the next topic, I guess you could say, in confidence intervals. What if we don't know the population mean, or excuse me, the population standard deviation? So let me rephrase it because I don't know if I said that right. So far we've assumed that we know the population standard deviation. So next thing we'll talk about in a little bit is what if we don't know the standard deviation. That's where we're going to introduce a new distribution to consider. Okay, so now as a review, let's do an example, and we're going to compare confidence intervals now. So what we're going to do is we're going to create confidence intervals, two different types of confidence intervals, and then what we'll do is compare them, and then see why are they different. And then we'll talk about minimum sample size. So let's see here. So the last example that we did, just to go back, is we did the example with the cell phones. And so if we continue with that, let's see, we found that the confidence interval, and we were doing a 98% confidence interval. And so the 98% confidence interval that we got for the SARS, yeah, that was it, for the SARS. The specific absorption rate for cell phones. And so we took that data, we plugged it into the calculator, and we used the function to get a confidence interval. And the confidence interval that we got was this. And we wanted a 98% confidence interval. Let's see here. Oops. So we wanted a 90, okay, the markers are not working. Okay, let's try this one. There we go. So we wanted a 98% confidence interval for mu, for the, which was the SARS, the SAR, SAR, the specific absorption rate for a cell phone. And let's see here. What do we get? We got yeah. So here's what we got. We got this interval using Z interval. Okay, and we knew that sigma, right? So we knew sigma was equal to 0.337, and we did a Z interval, right? And you could also use the formula. So let's just put the formula up there. So we know that since we know sigma, we know we're talking about the parameter mu. We know this is the formula that we need to use for the confidence interval. But we could also use Z interval on your calculator. And the confidence interval that we obtained was this, 0.8806 and 1.1674. And let me go back to the calculator just to double check that. Okay, hold on. Just so sigma's 0.337, and this was a 98, and I got something a little bit different, but I might have put my numbers wrong. Let me double check my numbers. Always double check your numbers. So stat edit. So 1.11, 1.43. Okay, so if I do it one more time, so data 0.337, 1.98, and calculate. Okay, so I got some there. I'm going to go with my numbers because that might be a typo. So 0.8806, 1.1669. That's what this should be. I think they made a typo. So 1.669. That should be the correct Z interval. Okay, so that's the 99% confidence interval. So we are 98. We are 98% confident that the true value for the specific absorption rate for all cell phones is going to be somewhere between 0.8806 and 1.1669. Okay, so that's the interpretation. So now, what if I wanted to find a different, well, what if I wanted to calculate something else? What if I wanted to calculate a 93% confidence interval? Okay, so let's calculate a 93% confidence interval for this one. Okay, so for a 93% confidence interval, from you, what do we get? Well, if we use the same function, all we have to do is just change the confidence level, and we'll do that. We'll say stat tests, number 7 for Z interval, and we're going to go back down, and we're going to change it to a 93.93. And now we get 0.91, and I'm just going to round these off. So let's do 3. So 0.912, so 0.912, and 1.135, 1.135, okay? And so what if we do a 90? Or let's do an 80. Well, not an 80. Let's do 0.8 for the confidence interval. And now we get 0.945. So for an 80% confidence interval from you, we get what? We get 0.945 to 1.103. Okay? And so what you notice here is if we keep everything the same and we increase the confidence level and keep everything the same, what do we notice is happening here? Well, if we look, right, if we look at the endpoints here, we notice that this endpoint is what? it's decreasing. So as the confidence level increases, this endpoint is going down. What's going on with the left or the right endpoint? It's going up. So what's happening here is the range, right? The interval is increasing, right? So the confidence interval is getting bigger as the confidence level increases. And why is that? Well, it should make sense if you remember the anatomy of a confidence interval. Always keep in mind the anatomy of a confidence interval. Well, what do we have? Well, we have two pieces, right? So if we have the confidence interval, right, we know it's x bar plus or minus z alpha divided by 2 times sigma over the square root of n. And remember, this is our point estimate, right? This is our point estimate here. And this is our margin of error. Okay? And so this stayed the same, right? That doesn't change. Sigma doesn't change. The sample size isn't changing, right? The only thing that's changing is this piece. Well, what controls that? The confidence level, remember? So the confidence level determines the critical value, right? And so what's going on here? Well, as the critical level is increasing, the confidence level increasing, look what's happening to the middle, right? Remember, what does the confidence level represent? It's the middle area, right? So if we look at the middle area here as our confidence level, well, as the middle is getting bigger, what's happening to these values? Well, what's happening to negative z alpha over 2 and positive z alpha over 2? Well, as the middle is getting bigger, this value is heading out that way, and this value is heading out the other way. So this is getting bigger this way, this is getting bigger this way. So the margin of error is getting bigger, right? Because the two values, plus or minus, are getting bigger, right? So that's one way to look at it. So if you just understand the relationship, then you'll know that, hey, if everything stays the same except for the confidence level, that means as confidence level increases, our interval is going to get bigger. Well, why is that? Well, think about it. Intuitively, if we want to be more confident that we have captured, remember the net analogy, right? If I want to be more confident that I'm going to capture the true value of the population mean, right? I should use a bigger net, right? So, in other words, if I increase my confidence, I'm increasing the net of values for the sample mean, which is going to make me a higher probability, right, of collecting the true value of the population mean in there somewhere. Okay, so that's the idea behind that. Okay, and I hope that makes sense. Okay, so now let's look at something else. Let's see what else we got. Okay, so we talked about that. Okay. Okay, so now this brings up another piece, right? So here's the thing. So let's erase this for a moment. And now let's focus on the margin of error part. Okay, so now notice that this is really going to stay the same for a particular problem. Okay, so the only thing that affects the width, right, the size or the width of a confidence interval is the margin of error. So let's take a specific look at the margin of error. Okay, so margin of error is going to be this formula. So we have margin of error is our z alpha divided by 2 times sigma over the square root of n. And so if the confidence level goes up, right, we know that it affects the margin of error. So as confidence level increases, this will also increase, which means this whole thing increases, right? But what else can change? Well, this is going to be fixed. That won't change. What about sample size? Well, sample size, we could use a different sample size, right? That can change. Well, how does that work? Well, what we notice here is what happens to our confidence interval as sample size increases. Well, let's just think about it. So if this is fixed, so let's say we have a specific confidence level, okay? And let's say this is fixed. The margin of error is fixed. Or excuse me, not the margin of error, I'm sorry. Not right now. So what affects the margin of error? Well, if this is going to stay fixed, and we know sigma is always fixed, well then that means we can change the confidence interval by changing the sample size. So what happens here? What happens if n increases and we use a bigger sample? Well, what happens to this fraction? Well, what happens to any fraction if the denominator stays the same, or excuse me, if the numerator stays the same but the denominator gets bigger? Well, what happens here? Is that fraction getting bigger or smaller as the denominator gets bigger? It's getting smaller. So what happens to this as the sample size gets bigger? Well, this fraction is going to get smaller. Well, if this fraction gets smaller, if this number here gets smaller, and this is staying the same, what happens to this whole product? Well, the whole product is going to get smaller, right? So that means the margin of error gets smaller as the sample size gets bigger. So what does that do to our confidence interval? It makes it smaller. So as sample size increases, our confidence interval gets smaller for the same confidence level, which means that if we increase our if we increase our sample size, keeping everything the same, then our confidence interval gets smaller, which means it gets more precise. We have less values, right, for the same confidence interval, or confidence level rather. Okay, so that's the other relationship. So as n increases, our margin of error gets smaller. Okay, so now that brings up our next topic about minimum sample size. So let's say I have a particular margin of error. Remember, margin of error is the maximum amount of error we want, right? It's the maximum distance away from the sample mean we want to be. So if we fix the margin of error at a particular value, and we say, hey, we don't want our margin of error to be any bigger than this, then the question then becomes is, how big of a sample size do we need to guarantee that it won't be bigger than the specified margin of error? Great question. That's where this formula comes in. Because all we're going to do is we're going to take our margin of error formula, in this case, and we're going to solve for n. So this is the margin of error, so n, our minimum sample size, becomes n is equal to z alpha divided by 2 times sigma over the margin of error, that whole thing squared, and this is our minimum sample size. And the thing about minimum sample size is we always round up. Always round up to the next whole number. Never round down. Okay? Why? Because if we round down, then we're no longer going to be guaranteed to be below the margin of error. So always round up to be conservative. So anytime you get a decimal, always round up to the next whole number. Okay? So just keep that in mind. So let's do an example. So here it is. It says the population standard deviation for the age of Foothill College students is 15 years. So the population standard deviation for the age of Foothill College students is 15 years. So sigma equals 15 years. Now, if we want to be 95% confident, there's our confidence level, right? if we want to be 95% confident that the sample mean is within, there's the key word, within 2 years, okay? Oh, so that means the margin of error is 2 years. We don't want to be any further from the sample mean than 2 years. So we don't want to be any more than 2 years below or 2 years above. So that's the margin of error. So the margin of error is 2 years. Okay, good. Now it says, hey, we want to be within 2 years of the true population mean age for Foothill College students. How many randomly selected Foothill College students must be surveyed? Okay, well, now we're going to use our trusty dusty formula, and there's no function on your calculator to do this, so you're just going to have to use the formula. So it's going to be this formula here. And all we're going to do is plug and chug. So now, does the critical value, okay, remember the critical value you can get using the calculator. You have to use the calculator or the table here. So you can use the table, right? So you can use the Z table, or you can use inverse norm. Okay? Either way, or you can remember it, right? Remember confidence intervals, those common ones. This is the most common confidence level. So if you use inverse norm or use the T table, you'll find that this is going to be 1.96 as your critical value. Okay? Sigma, we know, is 15 years, and the margin of error is 2. So this, right, the confidence level gives us our critical value, and then you could use the table or inverse norm to get the critical value. So now all we have to do is plug and chug. So this is going to be 1.96 times 15 divided by 2. And then we're going to square that. And so what do we get? Well, we get something very close to 15 squared. So it's going to be close to 225. Okay? So let's do that. So we get 1.96 times 15 divided by 2. And we square that. 216.09. 216.09. So how many students should we survey? Remember, always round up. So we should have a minimum of 217 students in our survey. Okay, and that's it. That's really it. So let's do this one. It says the population standard deviation for high school for the height of high school basketball players is 3 inches. Okay, so let's do this one. Okay, so the standard deviation for the height of high school basketball players is 3 inches. If you want to be 95% confident, so again, the confidence level is 0.95. We want to be 95% confident that the sample mean height is within 1 inch of the true population mean height. So again, we want to be 95% confident that the sample mean height, so x bar, that x bar is within, keyword within 1 inch of the true population mean height. Okay, so margin of error here is 1 inch. And so it says, again, how many randomly selected students must be surveyed? Okay, again, we're going to use our formula, n equals z alpha divided by 2 times sigma over the margin of error, quantity squared. Okay, now, again, the z alpha divided by 2 critical value is still going to be the same, right? So this value right here is still going to be 1.96, right? Again, you could use the table or inverse norm to get that for you. So it's going to be 1.96 times 3 inches. right? That's the standard deviation, and the margin of error is 1 inch. And we're going to square that. So again, we're going to get 1.96 times 3, and then square it. So it's almost, obviously this is close to 2, so this is almost 36. So it won't be quite equal to 36 because it's less than 2. So 1.96 times 3, and we're going to square it. So we have 34.57. So 34.57. So how many students do we need the survey? 36, or excuse me, 35. 36 would work too, but 35 is the minimum. So again, we would have to have a minimum of 35 students in our survey. So that's it. That's margin of error, okay? With minimum sample size, okay? So it's that straightforward. Okay, so now, next time, we're going to talk about the confidence interval involving the mean, right, the parameter mean, when sigma is unknown. And what do we have to do there? Well, that's where we're going to introduce the t-distribution, and we're going to talk about how we use that to do the same thing, calculate or construct the confidence interval. Thank you, and we'll talk soon.